is going to be R2 dot transpose T2 of 2 omega I cross 2 gamma. And this is going to be equal to 0, -3 theta 1 dot sine of theta 1, 3 theta dot 1 cosine theta 1 transpose times rho x of theta 1 plus theta 2 all times theta 1 plus theta 2 dot, 0, 0, which is 2 omega I. Let me check something real quick. Okay, yes, 2 omega I cross 0 gamma x theta, because we only have rotation about x, remember, when you're looking at this frame. This is only a rotation about x, so all you'll have is the gamma x and jxx, that kind of thing. So then this is going to be rot x of theta 1 plus theta 2 times this thing still of 0, 0, 2 gamma y of theta 1 dot plus theta 2 dot. Just like that. This thing keeps on carrying down. And it's going to be times again 0 of 2 negative gamma y of theta 1. Sorry. Didn't take that down far enough. Times 0 times negative, 2 gamma y of theta 1 dot plus theta 2 dot sine theta 1 plus theta 2 2 gamma y of theta 1 dot plus theta 2 dot cosine of theta 1 plus theta 2. Okay. And if you multiply that by this now, up here, the final coupling energy will be 3 times 2 gamma y of theta 1 dot squared plus theta 1 dot theta 2 sine theta 1 plus theta 2 sine theta 1 plus 3 2 gamma y theta 1 dot squared plus theta 2 dot theta 1 cosine, continuation on down here, theta 1 plus theta 2 cosine of theta 1 dot down to here. Make that an arrow so you're not confused. Alright, so that's set up. For the final part now, all we have to do is do 1 I transpose 2 j of 2 omega I. And if you set this up, you'll end up with 1/2 theta 1 dot plus theta 2 dot 0 transposed times 2 j x, and then so on, so forth, so on, so forth, so on, so forth, so on, so forth. However big that'll be. In this case, it's going to be a 3×3. But again, we have the setup where you have a transpose times a matrix times the non-transpose. And what happens is you end up basically just taking the upper left-hand corner of this matrix, which is jxx. Well, that's not always the case. But the transpose of this times this, and the fact that they both have zeros afterwards means you're taking the upper left-hand corner of it. So this will be theta 1 dot plus theta 2 dot 0. These zeros, this is all in the upper top, times the transpose, times the normal one, times the matrix, so on and so forth. You only grab this one, so then the answer to this will then be 1/2 of theta 1 dot plus theta 2 dot squared 2 jxx. And this is the rotational energy. Rotational, and this is coupling So now the total equation for kinetic energy, I'm going to write it sideways here because it's really long, is K is equal to K1 plus K2. And K1, previously we had solved for it, and we found out that it was this value up here is equal to K1. And then each one of these components that we had previously are the other bits and pieces of K2. So if we add that all together, basically, just add all of these pieces together, you'll end up with K is equal to, let me get you set up. All right, K is equal to 1/2 of theta dot 1 squared 1 jxx plus 9/2 theta 1 dot squared m2 plus 3/2 gamma y of theta 1 dot squared plus theta 1 dot theta 2 dot times sine of theta 1 plus theta 2 sine of theta 1 plus cosine of theta 1 plus theta 2 times cosine of theta 1, and then close this big main one. I'll actually make this a square one, make that a little bit clearer, plus 1/2 of theta 1 dot plus theta 2 dot squared to 2jxx. And that is your total and complete kinetic energy for this robotic system right there. Basically, you find the kinetic energy of each piece by using the equation that you can use based on the information that you have, and then you go to town solving matrix equations, basically, or vector equations.